This video is an introduction to a series of short videos relevant to freshman students' physical chemistry. The series will cover 4 worked examples of solving the reaction rate laws given a proposed chemical reaction mechanism. After this series of videos, you should be able to identify intermediates in a reaction mechanism, apply the steady state approximation to intermediates and obtain expressions for their concentration, derive rate laws given a mechanism, and finally, given a slow step in a reaction mechanism, identify if it's a rate determining step, then immediately write the rate law if it's the case. What's relevant to this particular topic is that you need to know the following: that the rate determining step controls the overall rate of a reaction. The rate determining step is the slowest step in the mechanism, but it's important to note that it just doesn't have to be the slowest step because it might only be marginally slower than some other step. It really needs to be considerably slower than all other steps. And that for it to be a rate determining step, that is this particular elementary reaction, if it's to be a rate determining step, it must form a crucial gateway for the formation of products. That is to say, there's no other possible alternative route that can circumvent this particular step. Steady state approximation, we'll be using that on several occasions. The steady state approximations when all the intermediates of a reaction mechanism have their net rates of formation approximated to 0. And we can only really expect this approximation to be accurate when the concentration of intermediates is comparatively low during the course of the reaction. And finally, we'll be using this on several occasions for the reaction rate. So for any particular reaction, and here's a general one, so the lowercase letters are stoichiometric coefficients. The capital letters are representing chemicals. So the overall rate of reaction, just by being given this summary reaction here, can generally be written in this form. So for reactants, we'll have this type of form, and for products we'll have this type of form. Regardless of which chemical we end up focusing on, the rate of reaction will always be positive and the same. And the units to note for rate of reaction is given by moles per liter or molar per second. The 4 examples we'll be covering, the first is looking at devising a rate law for the decomposition of nitrogen pentoxide. And here's the overall summary reaction, and here's the proposed mechanism for which this reaction proceeds. The second example, we'll look at deriving a rate law for the decomposition of ozone. And here's our summary reaction, with this being the proposed mechanism. Note that the mechanism need not be actually the one that's occurring. This is a hypothesis. This is a proposed mechanism, and from that proposed mechanism, one can derive a rate law, and then one would compare this rate law to the experimental findings regarding the rate of decomposition of ozone in order to establish whether or not it's a reasonable mechanism. The third example we'll be looking at will be deriving a rate law for the oxidation of nitrogen monoxide to nitrogen dioxide, and we'll have these 3 steps as the proposed reaction mechanism. And finally, we'll be using the same overall reaction, the oxidation of nitrogen monoxide to nitrogen dioxide, using the same 3 steps, but this time we're told that the Ford's reaction is quite slow. And if it is a rate determining step for the reaction, can we immediately write down a rate law for the overall reaction? So those are the 4 examples we'll be looking at in these videos. I hope you'll join me to take a look at the first example in the next video on this playlist.